Thanks.
It's okay.
So let's talk about batteries. Batteries are very, very practical electrochemistry. They are voltaic cells that are conveniently packaged as portable sources of electricity. I mean, stop and think about that. Batteries are amazing, absolutely amazing. So there are different kinds of batteries, and they use different types of reactions, different chemical reactions. So dry cell batteries, these are an older style of battery. They are called dry cell because they don't have much water in them. So the oxidation reduction there is the oxidation of zinc. The reduction is the oxidation of manganese 4 oxide. So let's look at, I'm looking at the slide trying to figure out what I'm supposed to do with this. We're supposed to add those and look at the overall reaction. So we can add these two together with the 2 electrons here and the 2 electrons there. So we've got solid zinc and 2 MnO2, also a solid, and some aqueous ammonium. And that's going to react and form zinc ion, Mn2O3 solid, ammonia gas, and water. So these 2 half reactions together produce a voltage of 1.5 volts. You've got a moist paste of the MnO2, the ammonium chloride. There's a zinc case, and we have a graphite rod acting as the cathode. And so there's not liquid in this battery, and that's why it's called a dry cell. So we're going to be talking about the different types of batteries. I am not going to expect you to memorize a lot of information about them. It's more for your general information. Alkaline batteries are more familiar to us. They are a type of dry cell, but here the half reactions are occurring in basic medium. As the name suggests, alkaline. So these are basic batteries. So it is really a similar reaction of zinc with MnO2, but because it's in basic conditions, it's a little bit different. So we can add these two together. The electrons, of course, cancel out. The hydroxides cancel out. And so we're going to get zinc metal plus 2 MnO2 solid and 2 H2O liquid. And that's going to make zinc hydroxide. That's a solid, plus this interesting compound of manganese. Oh, and that's it. Sorry. That's a weird looking chemical formula, isn't it? So that's an ionic compound that has 2 different anions. And those things do exist. We just completely ignored them in Chem 1A. So these batteries are set up similarly to the acidic dry cell batteries. So you've got a graphite rod in the middle acting as the cathode. You've got the zinc anode along the outside, and you've got MnO2 in potassium hydroxide paste in between. So you've got a positive terminal, a negative terminal, and when you connect those terminals, the chemical reactions that are spontaneous will occur. There's a voltage difference of 1.5 volts, and electrons will flow if they are able to flow. If the ends are not connected, then the battery just sits there waiting for you, right? If you throw these in a box and there's a bunch of other stuff in there and there's somehow a circuit that gets completed between one end and the other, the reaction will occur and the battery will discharge without doing anything useful. Right? Lead acid storage batteries, these are the sort that are used in automobiles. These consist of 6 cells that are wired in series. Each cell produces 2 volts, and by putting them in series, they add together and you can get a voltage of 12 volts, which is generally what's needed to start the engine. So here we have, they're lead acid because they've got lead and acid in them, right? Such clever names these things have. So let's look at this overall reaction. So we've got, we can cancel out the electrons. And there's one hydrogen ion here, so we can get rid of one of those. Anything else? I don't see anything else canceling out. Okay, so then we just try to put this together. So we have solid lead, and we've got hydrogen sulfate ion. And hydrogen sulfate ion is showing up as a reactant in the oxidation and the reduction reactions. So there's 2 of those. And then we've got lead 4 oxide and 2 hydrogen ions. Then over here as products we have lead sulfate in both as products. So 3 lead sulfate, that's solid, and liquid water. So both of the electrodes produce solid lead sulfate, and if that reaction runs too long, the lead sulfate will coat the electrodes, and then it doesn't work very well anymore. So the basic way this is set up is you've got the anode is a lead grid, and it's got finely divided spongy lead packed into it. The electrolyte is 30% solution of sulfuric acid, and the cathode is a lead grid that's packed with lead 4 oxide. And you've got your terminals up here. The older lead storage batteries, maybe it's not this kind. The older car batteries used to have to add water to. I kind of think this one you maybe don't. But can you see why they don't want those in landfills? Full of lead and sulfuric acid. Not good for the environment, right? And if your battery is old and it's got crusty stuff hanging on it, should you be touching that with your bare hands? No, because it's most likely acid, right? So these batteries are somewhat hazardous. When they're running fine in your car, they're fine, but you don't want them outside the car in the landfill. So the lead sulfate will coat the electrodes, and then it doesn't work so well. The battery is recharged using electrical current. So it's a voltaic cell. This is the forward reaction. It's spontaneous, but eventually it'll wear down and won't give you much voltage anymore. And so you recharge it by running electric current into it the other way and forcing the reverse reaction to occur. And so then you can get it back to its starting point for the most part. And that's what the alternator in your car does. So the battery in your car is used to start the car. In the old days they had a crank, and you had to go out and crank the engine. So the battery gives the initial impulse of energy to start the car, Once the engine is running, the engine generates electricity, and that's what's running your headlights and your radio and stuff. The alternator also is going to direct some of that energy into the battery to recharge the battery. So that's why if your alternator is going bad on your car, the car will still run, but the battery won't charge, and eventually your battery will go dead. There are other sorts of rechargeable batteries, nickel cadmium or NiCad batteries. Obviously those have nickel and cadmium in them. So the anode is solid cadmium that gets oxidized to cadmium hydroxide. The cathode is, I'm not exactly how to say the name of that, NiOOH. It's another one of those weird compounds that has two different anions. That gets reduced to nickel 2 hydroxide, and the overall reaction produces 1.3 volts. So again, solid products build up on the electrodes, but you can recharge them by running current in the opposite direction. If you overcharge a nickel cadmium battery, then you produce other reactions that actually damage the battery. So overcharging of rechargeable battery is not a good idea. So a good battery charger will have a sensor in it that will stop the charging when the battery is fully charged. Nickel metal hydride batteries. Nickel cadmium batteries have cadmium in them. Cadmium is a very toxic metal, and so that's not desirable. So the nickel metal hydride battery has the same cathode reaction, but a different anode reaction. And so it's got hydrogen atoms held in a metal alloy, and those get oxidized. Another benefit is this has greater energy density, meaning you have more energy content per unit of battery mass. So you'll get longer life for your device for the same amount of battery mass. And who wants a super heavy battery in their pocket? Nobody. Lithium-ion batteries. These are newer and they are more expensive. But these are the batteries that are common in cell phones and laptops and digital cameras and all those good things. They have high energy density, so lots of energy per unit of mass of the battery. And these work differently. Here we've got the lithium ions that are moving from the anode to the cathode, and that causes electrons to move through an external circuit. So it's a little bit different than the other sorts of batteries. Then we have fuel cells. Fuel cells, in a way, are like batteries, except instead of recharging them, you replenish the reactants. So the hydrogen-oxygen fuel cell is the most common. You've got hydrogen gas that flows past the anode and gets oxidized, and oxygen gas flows past the cathode and gets reduced. The product of that is water, which is great because it's non-toxic. But you need a source of hydrogen and a source of oxygen. So they are not all that practical right now because where do you get the hydrogen? The source of hydrogen is kind of the holdup right now. Here's a diagram of the cell. There are cars that run on hydrogen-oxygen fuel cells. But again, getting the hydrogen is an issue. So we've got this electrolyte, and we've got, what do we have going on here? We've got oxygen gas and hydrogen gas coming in, and the hydrogen gets oxidized, the oxygen gets reduced, and so the products that are formed are water. I don't know what else to say about that. There it is.